Welcome to our discussion on incentive design once again. So, in our last class yesterday we were talking about the efficiency, effectiveness and equity properties of these two main instruments, market based instruments, particularly emission charge and tradable pollution permit. And then we said that depending on the social planners or policymakers objective, we have to carefully select either emission charge or tradable pollution permit. We said that when the policymakers objective is to maintain certainty over cost of pollution control, then emission charge is preferred to market based instrument, while tradable pollution permit is preferred when the policymaker's objective is to get a fixed amount of pollution in a given period of time. And we have also discussed about the efficiency, how the emission charge is basically efficient compared to uniform standards, right. Now, what we will do today, so this is basically we are talking about in detail little more about the efficiency property of emission charge. Why once again we are discussing the efficiency property, I will discuss and I will explain to you in detail. So, this is efficiency property of emission charge. So, by efficiency what do we mean? We said that efficiency is achieving targeted level of emission reduction at minimum cost. Now, when you are saying achieving targeted level of emission reduction at minimum cost, what is exactly the cost we are talking about here? By cost, we mean actually what we are minimizing? Minimizing social resource cost, right, social resource cost. And the interesting point here is to mention why the society is bothered about what is the resource cost here, because resource cost involves some amount of resources which are diverted for pollution control, which could otherwise been used for making goods and services. Is this clear? So, that means the moment society wants to achieve pollution reduction, so that means society is imposing some regulation, let us say that in this case in the form of emission tax, and the firms what they are doing, the firms are diverting some of their resources for pollution control. So, that means the inputs which were earlier used for let us say there is one input, let us say labor and capital, those are used earlier, they were used for making goods and services. Now, some part of your labor, some part of your capital is now diverted for pollution control. Okay. Similarly, the firms are also buying some specific inputs, let us say some end of pipe technology for pollution control, and that also involves some amount of cost, and society wants to ensure that this cost, this resource cost for pollution abatement should be minimum. Why the society wants to achieve that? Because higher is the cost of abatement, higher would be the price of the product, and the private players will try to bypass some amount of cost to the consumers. So, consumers, they have to pay higher price for their product the moment regulation is imposed, right. So, that means there is a private cost, there is a social cost, right. Private players, the firms, so that means the moment tax is imposed, what is happening here? The emission tax what happens? Emission tax helps align private cost with social cost. Private cost with the social cost. That means the reaction of private players, the reaction of these polluting firms when the tax is imposed coincides with the social planners' objectives. That is why we say that this emission tax helps aligning private cost with the social cost. So, that means private objective with the social objective, right. That is what happens in the form of emission tax. So, what we believe a tax, emission tax set at a level to achieve a targeted level of pollution control, pollution reduction, minimizes social cost. Of pollution control. So, this is basically a theorem given by famous economist Baumol and Oates. So, in terms of a diagram, if you look at the diagram what we have discussed, that this is the industry level and society wants to achieve this much of pollution control. So, here what we have to do, so that means when this T star is fixed at a level, so this is MSE B, this is MSE A. So, A will reduce this much of pollution, B will reduce this much of pollution, and that is better than the uniform standard E bar. Okay, and this is let us say half of EFA plus EFB. So, a tax rate which is set at a level T star that achieves the targeted level of pollution control, which is half of EFA plus EFB, minimizes the social cost of pollution control. That is a theorem Baumol and Oates said long back. And what is the social cost of pollution control? Basically, we are talking about minimizing the resource cost, right. So, in this case, what is the assumption what we are making? The assumption what we make here is that in the process of pollution control, we use some inputs which again does not generate any other form of emission. For example, let us say we are generating some garbage and there is a garbage incinerator used to recycle that waste, and the garbage incinerator again is not discharging some other form of emission. If that is the case, then this theorem is actually not valid. So, that means we are ruling out the possibility of any other form of emission again in the form of pollution control. If that assumption is valid, if there is no other emission, then the reaction of the private player to this tax, emission tax T star, which is imposed by the social planner or the policy maker, that achieves the targeted level of emission reduction, which is half of EFA plus EFB at minimum cost. Okay. Now, how is it happening? Because every firm is basically equating their marginal cost of abatement with the tax rate. Now, we got a graphical and intuitive explanation of this particular theorem, that when this condition is satisfied, that means when T equals to MSE A equals to MSE B, when both the firms are equating their marginal cost of abatement with the imposed tax rate, then social cost of pollution control is minimum. But we have not yet got any formal proof of this theorem. So, what we need to do now? We need to have a formal proof of this theorem. Why we are interested in that formal proof? Because then only we will understand what the social planner's objective in the process of pollution control, what is the objective of the private firms, and how this tax rate is actually helps coinciding the private firm's objective or objective function with that of the social planners. So, social planner is also interested in some kind of cost minimization, private firms is also interested in some kind of cost minimization, both are trying to minimize their resource cost, and tax rate is helping them aligning private cost with the social one. How is that happening? That we will now try to understand. So, that is basically a formal proof of this Baumol and Oates theorem. Okay, formal proof. Right. So, first we will discuss about what is the social planner's problem. Social planner's problem. Okay. So, we assume, let us assume there are let's assume that there are k number of firms in an industry. Okay. Each firm is producing some output and the production function is given by production function of the kth firm. Let us say the production function of the kth firm is given by, let us say, production function is given by R1k, R2k, R, let us say, in k. Okay. So, that means what is R1k? R1k is basically the first input used by the kth firm, R2k is the second input used by the kth firm, and Rnk is the nth input used by the kth firm in this production process. This is basically the production function, right. And then there is some kind of emission function also. Each firm is generating some kind of emission, and that emission function, emission generating function is basically, emission is a function of what is your output at optimum plus some abatement input, right. So, this is production function, of kth firm, and this is emission function okay. And this Vk is the abatement input, Vk is the abatement input, Vk is abatement input. Right, abatement input. Let us say the kth firm has installed some kind of end of pipe treatment technology, and Vk is the abatement input. Now, what the social planner will try to minimize then? The social planner's objective function is to minimize sum of production cost, that means Pi Rik plus summation PV into Vk. Okay, and this is I and this is K. So, if you look at, so Pi is price of ith input, and PV price of abatement input. So, that means in the social planner's objective function, what we are seeing, that this Pi plus Rik, that means there are k number of firms and each firm they are using n number of inputs. So, when I am taking double summation, first summation is basically summing over input, second summation is the summing over firms. So, if I take double summation Pi Rik, that captures all the firms input cost, and here this is only summing over firms. That means each firm is using only one abatement input, that is V, and price of this is PV. Okay, right. So, this captures the abatement cost of all the firms. So, social planner is trying to minimize, that means cost of production plus cost of abatement, right. This is the objective function. And what is the condition here? Subject to social planner wants there is some kind of optimum input for the kth form, that means this is let us say R1k, R2k, right, and then Ek equals to the emission function, which is again, and total emission should not exceed, total emission should not exceed sum of Ek, this, right. So, social planner wants to minimize total cost of production plus total cost of abatement, subject to these are the restriction that kth firm should produce a given level of output, this is the emission function, and total emission should not exceed some E bar amount. And here what we assume that Ek is positive greater than 0 for all k, right. So, this is the social planner's problem, and what we need to do? We need to set a Lagrangian function. The Lagrangian function, for cost minimization. What is the Lagrangian function for cost minimization? Let us say this is L is the Lagrangian function equals to, first we have to write the objective function summation, double summation actually Pi R I k, this is I and this is k, plus PV into V k summing over k plus some lambda k into y k star minus f plus another Lagrangian multiplier which is let us say mu then sum of this b k minus E bar. Okay. Right. So, there are two Lagrangian multiplier here, one is lambda k and another one is mu, right, another one is mu. So, first we will try to derive the condition mechanically, and then we will try to understand what is basically this lambda k and what is this mu, right. What is the interpretation of these two Lagrangian multipliers? This is summing over k, which is coming from this function actually. It should be sum of Ek minus this, and Ek is, since Ek is given by this function, that is why we have written sum of b function this. And what is our control variable here? The control variable here is Rik, that means amount of input which is used for production and amount of input which is used for abatement. Rik and Vk, these are the two control variables. So, that means the minimization requires that differentiating this Lagrangian function with respect to del Rik and set it equals to 0, and that implies that Pi minus this lambda k into del f k del r I k equals to 0. So, that means I can write P I equals to lambda k into del f k into del r I k. This is one condition. And second condition is differentiating this Lagrangian with respect to V k equals to 0. And if you do that, then you will get P v equals to minus of mu into del B k del V k. Now, here since this is there is a negative sign here, and if you think about this, what is del B k del V k? That means change in emission for a change in abatement input. And when you increase the abatement input, the emission goes down. That is why this also negative, this negative and this negative will turn out to be positive. So, that means P v equals to this. Let us say this is equation 1 and let us say this is equation 2. So, these are the two conditions we derived from the social planar subjective, right. Now, we have to see what the private firm is trying to do. Form subjective. So, we said that the moment tax is imposed, private firm's objective function will coincide with the social planar subjective. So, that means in the form subjective also we will get the same component of same objective function which we can borrow from the social planars one. Additionally, the private firm what the private firm will try to incorporate in that objective function is the tax amount, because anyway the resource cost is derived from the firm's point of view, and for that in that process the firm will include the tax amount also to get total cost. So, that means the firm's objective would be minimize sum of double summation I and k, then I will write P I R I k plus P v into V k, this is common, plus the tax rate which is imposed at T star level to achieve that targeted level of emission. And how much is the tax? The amount is decided by your optimum amount of production and the abatement input, right. And what is the condition here? The same condition, y k star is given by the production function, and then E k is basically B k function, and E k also greater than 0. So, this is form subjective. The first two components were there in social planar subjective also. This additional component, this is the tax T star multiplied by amount of emission, which is decided by your optimum level of output and the abatement input that you are going to use, right. So, again the Lagrangian function for cost minimization. Lagrangian function for cost minimization, L equals to, we will write double summation P I R I K, this is I, this is K, plus summation P V into V K to V K plus T star into B K plus the Lagrangian multiplier. Let us say this is the Lagrangian multiplier which is this Y K star minus f of this. This is the Lagrangian multiplier. Okay. And again, if you differentiate this with respect to del R I K and set it equals to 0, then what will get? That it will give you P I equals to, so this R is here only this function. So, that means equals to beta k into del f k del R I K. Let us say this is equation 3 and del L del V K, if you set it equals to 0, that will give you where is V? V is only here in this production function. So, that means P V would be equals to T star P V equals to, that means minus T star into del B K into del V K. Again, since this is negative, this would become positive. Okay. This is 4. All right. Now, since the tax rate helps coinciding firm's objective with the social planners one, now by equating equation 1 and 2 with 3 and 4, what we will get? So, that means if we say that this 3 is equivalent to 1, this 3 is equivalent to 1, these 1 and 2, basically these 2 are equivalent to 3 and 4. Look at the condition, we are getting P V equals to this, okay. P V equals to, so this is also become plus. So, that means we will say that here we are getting P V equals to this and mu into del B K del V K, right, and here we are getting P V equals to T star into del B K del V K. So, from these two, what we can write? From 2 and 4, what we can write, that T star is actually T star equals to mu. T star equals to mu. And what is T star from here? From 4, what we can get? 4 says that T star is actually equals to minus of P V divided by del B K del B K. Since this is negative, this will become positive, right. All right. So, What is the meaning of this PV divided by this? So, this particular mathematical expression, it has some meaning. What is that meaning? We will try to understand. See, first of all, del Bk del Vk is basically indicates change in emission for 1 unit change in Vk. That is what it means, del Bk del Vk. So, change in emission, because the numerator is basically emission function. So, the moment you differentiate that with respect to Vk, what you can get, that this is nothing but change in emission for 1 unit change in Vk. Suppose I am increasing the abatement input. If I buy one additional abatement input, what is my cost? My cost is PV, because that is the price of abatement input, right. So, that means indirectly I can say that to get this amount of change in emission, my cost is PV amount. I am repeating this once again. This indicates change in emission for 1 unit change in Vk, and 1 unit change in Vk costs PV amount. That is why I can say for del Bk del Vk amount of change cost is PV for 1 unit. So, for 1 unit change in emission, cost is PV divided by this del Bk del Vk, and that is nothing but for 1 unit change in emission, the cost what I incur is nothing but marginal cost of abatement for the kth firm. So, that means this is nothing but T star equals to MAC, marginal cost of abatement for the kth firm. This is nothing but marginal cost of abatement. Since we assume K is a representative form, we assume K is a representative form, this is true for each and every firm. So, that means the condition what we have derived, that cost minimization requires equating marginal abatement cost with the tax rate, that is true for each and every firm, and that is what we are talking about earlier, that T equals to MAC A equals to MAC B. If that condition is satisfied, that means at that condition only society can achieve targeted level of pollution reduction at minimum cost. This is the formal proof, because this condition is derived from this cost minimization only. Additionally, what we have assumed, that a firm's reaction to the emission tax helps coinciding the social planner's objective with the private firm's objective, right. Is that fine? So, that means at optimality each firm will equate the imposed tax with the marginal abatement cost, and that will help targeting achieving the targeted level of emission tax at minimum resource cost. Now, what I said earlier, that this is the mechanical derivation of the condition, but since this process of minimization requires Lagrangian multiplier, we have not understood actually two things. When I said that this is the Lagrangian case, so what is the meaning of this lambda k and what is the meaning of this mu? These are the interpretation of lambda k and mu. These are the two Lagrangian multiplier we have used. We need to learn the economic interpretation of these two Lagrangian multiplier.